HR director here in Provectus. And here is Anna. Yes.
Yeah, I'm an employer brand manager at another IT company here, Provectus. We'll talk about them a little bit later.
Yeah, why we came to this idea to create the Wroclaw IT community, and what is it? So now we are in our office. This is our office space process. We came here after the active phase of war started. Provectus is IT community, IT company that was based in Kiev, and we had the biggest part of our team in Ukraine previously, and then after war started, we came here, and previously we had like a small transition, like a temporary office in Antalya. We moved this part of our team there before start of war, and then we decided to came to the plan B, and we chose Wroclaw as our location in point. So we are here starting from March 2020, and then in May. We with my colleague went to conference in Gdańsk, and we met guys. Guys are here, Alexey and Sasha. They are from Provectus, and we realized that we both we were in Gdańsk, but we realized that we both came to Wroclaw. We chose this location to set an office, to set new location for our companies. They are from Odessa, we were from Kiev, and then we decided that, okay, it's cool, we met there, and we decided to make some collaboration. We met here in Wroclaw, and then Alexey asked whether there is some community in Wroclaw, technical community, where we can meet, somehow communicate, participate, somehow have this network and meet people who are Ukrainian or from other countries, and of course from foreign. And we realized that there is no such community, unfortunately, and there's no place to meet and to share somehow this IT network. So we decided to create a new one, and we made this collaboration together like partners. And Anna,
Yeah,
maybe our plan.
And you're lucky to be here at this very first Wroclaw IT community event, but we are hoping to have this community developed and to have events like these once every 1 or 2 months. And we would be really glad if you help us to spread the word about this community. That's why you have these little papers, those of you who took them, of course. We'll have this little activity. Those of you who want to get the guaranteed little things, these are the cheat sheets, the posters on different topics like data science, Python, DevOps, and machine learning. Like you can pick one. So whoever shares a story or a post to Instagram or Facebook from this event, like it can be whatever, like any speaker, any coffee break, like whatever. You just need to tag our companies, Provectus Live and Proxit Nation, and then just come to me or Ina, and we'll give you one of these things. And also, we will choose randomly 3 people out of those who participated to get some other prizes like T-shirts, cups, and stuff like this. So please, please join, not only for the prizes, but also for the spirit of the community.
Yeah, and also I'd like to mention that today's our topic is the science and data engineering. You obviously saw the our agenda, but also we want to create a space for different topics and to organize events with other technologies or other topics, and we have some plans for November, and then actually we are really welcome if any of you wants to share some of your experience or somehow participate in this activity and be a speaker. feel free to reach out to us, and we can organize and involve you in this activity. Or maybe you know some cool speaker who you want to meet here. We also can adjust such event. So,
and can you please put another slide?
Okay, yeah, we had slides. Actually.
Yeah, there just 3 of them is still, and one of the slides, yeah, presentations are not the strongest part here, not for us. Okay, doesn't work.
Okay, the next slide is this text.
Yeah,
you can read something there. Okay, here is it. But we can move to the next one.
I'm trying. I'm really trying.
Okay, and this is there will be let's work. QR code to link to our community because we want to share it. This is the very first event we are making here, and we want really to collaborate and to gather people in Wroclaw to meet, to learn something new, obviously, and to communicate. Okay, I guess we can start. First speaker is Alexey. Welcome, Alexey.
So hi guys, I'd like to welcome you to our first event of Wroclaw IT Community, and I will talk about data engineering and one of the use cases I participated in. But like first of all, yeah, our community would be in English, but please raise hand who participated previously in communities on other languages. No? Okay. It would be, yeah, interesting to hear your feedback going forward. So let's start. A little bit about myself. So currently I'm a delivery director of Data ML and Cloud in Provectus. Previously I was a data solution architect and engineering manager. Had something like 14 years of experience in IT, in leadership for a while. In my spare time, I like to do sports like CrossFit, extreme sports. And interesting thing about me is that I wrote the code for the car that I'm currently driving. Yeah, it was 8-9 years ago. I had been into AWS for quite a while, got 3 certifications, and also participated in 3 game days, worldwide challenges, 2 of which we won, so took the first place, and earlier this year we took the 3rd place. Okay, a little bit about our company, so I won't bother a lot. It's not an onboarding meeting. So we have a lot of offices worldwide, and because of current situation, geopolitical situation, we opened several new offices, including Poland. We are on the market for 12 years, and currently we are slightly above 600 people. Yeah, we are AWS premium consulting partners with competencies in machine learning, big data, DevOps, and migration. Have a lot of programs for our clients, and here are example of some of the clients, and I believe that you're quite familiar with some of those logos. And today I will speak about one of them, so specifically IMVU, but I'll tell it about them going forward. So for Provectus, building the community is not something new. We, for quite a while, are really into open source, so we have our own products. Please check them out in our GitHub repository, which we are distributing under Apache license. Those are in 3 of our main verticals, which is like DevOps, data engineering, and machine learning. So join the community as well, participate in open source. It's quite fun, I believe. So, no? Yeah. So agenda for this talk is as follows. So I would tell about the client, about the initial research and architecture, and to be completely frank with you, so it was like initial agenda for this presentation, but coming up with the slides, I realized that if I would tell all about this specifically case study, it would take me like 2 hours. So I decided to break it up into parts. So today it would be mostly about the initial research, feasibility study, and first architecture. Yeah, and the purpose of the speech. So so you would be motivated to hear me for quite a while, and it's not easy deep technical topics. So I want to provide you with initial knowledge in change data capture, which is like concept that getting traction, a lot of traction lately in a variety of clients, especially clients with legacy infrastructure, trying to modernize those and receive advanced data and analytics, provide like good starting point for your deep dive, and yeah, and in general provide you with a little bit like framework of how you could do such architectural researches, which I would show you, and well, how it's done, so you could provide similar in your career. So, but let's get real. And actually, this is not like a random picture, because today we are talking about IMVU, which is 3D social network, some child of Facebook and Teams, where you're able to do your 3D avatar, participate in variety of like chat rooms, in events. There was also like online concerts, if I remember right, even like Madonna level concerts within this game. But they position themselves as a social network, and they're quite well on the market, but getting a special traction during the pandemics. So here's like slides from 2021, and they're like among top apps, mobile apps in United States and worldwide. Okay, yeah, few words about IMVU itself, some numbers. So they have like 200 millions of registered users, 7 millions of monthly active users, with something like around 2 million daily active users. They have more than 400,000 of 3D rooms, which are like chat rooms. 50 millions of items in their catalog, so you can go shopping, buy the actual clothes, take on your avatar. A lot of active creators for both like rooms and clothes, and average time spent during the day is 55 minutes for each of these users. And basically, this was the last official numbers that I were able to find, and those are 2020. And when we started the project, the numbers that I heard from within IMVU, but that were not shared, is that they had 16 millions of monthly active users and up to 10 millions of daily active users during like special events. As you can imagine, it's a lot of load on servers itself, and it's a lot of load to analytics to get this thing moving. And here is an example of mobile app interface, and actually this is like my account there. I try to be like similar. I don't know if it look alike, but at least I tried. So, and the last but not least, it was founded in 2004 by 4 founders, and one of their founders, Eric Rice, is the guy that wrote the book Lean Startup. And he wrote this book about IMVU. So IMVU is the Lean Startup that were in the book, and if you read it, there are also examples of these 3D avatars, which are actually in this app. And even like it was like during our work, they started to be like even bigger, organized into Together Labs company, which aggregated IMVU as one of them. Plus they have their own coin, crypto coin, Bitcoin, which one you can also pay in the game. They have their NFT part, MetaJuice, so you can buy drone outfit and be and it would be like your intellectual property, sell it afterwards. And of course social connections, which is IMVU, and you app called With Me, which is like more cartoonish or slightly younger audience. But let's get more technical. What we faced in IMVU from the start. So to get all these things moving, they had 58 databases. And it's not 58 tables, it's 58 databases combined in the cluster. And it were more like proprietary technology they've built internally, including sharded databases. So it was spread across more than 130 database instances on premise. No cloud in 2004, as you can imagine. Totally, we tried to calculate what the total amount of data there, and it was slightly like 380 terabytes in all those databases. And when we started our work, the one request, initial information for the request was that there are daily dumps for those databases from which they were getting analytics took up to 16 hours, which is kind of too much for daily analytics. So including processing of this data, you receive insights from yesterday, only tomorrow. Like it's a Ukrainian joke, it's like the mayor of Kiev, that type of thing. But, and yeah, their main ETL pipeline contains of about 500 jobs, which is Hive, Spark, Presto jobs, which are getting insights about all the events happening in this social network game, trying to optimize the income from selling goods, well, variety of things, basically. Yeah, a little bit about the preface for this case study. Initially, we participated with IMVU with cloud migration. So we migrated their Hadoop cluster to AWS EMR, and that's where was our first engagement. I won't stop on this use case, but still it's important to understand that we migrated their cluster in cloud setup, Cloud Kafka. It's something that we kept in mind while discovery and implementation phase. And yeah, I've left case study link in the presentation. If you would be interested, you could go there afterwards. We will share the presentations, by the way. Yeah. Okay. So finally, yeah, big data world. So the initial request. So as I've said, we were engaged with client for quite a while during the migration, which took somewhere between half a year and a year. And it was relatively fine on that stage for their daily dumps. It took only 8 hours. They didn't care about it. Yeah, because well, 8 hour dump, you receive it in the beginning of the day, right? So you can work with it. It's not a real problem. But in 2021, they got a lot of traction. It started to get 16 hours, and it was like too much for their management. So the main request was drastically improve the performance of processing daily analytics. But they had also a lot of limitations because, as I've said, those databases was on-prem and their analytics was already in the cloud. Yeah, because of the migration. So the limitation that guys shared us before this engagement is that they have MySQL 5.5. Update is not possible. Master database producing statement-based bin logs. I will talk about what does it mean going forward, but it could not be changed. Tools that pull data from on-premise are not allowed because of compliance reasons. They call personal data. There is no connection of on-prem environment like to the cloud. So it's like, well, on-prem has connection to the cloud, but not vice versa. So only push and last but not least, adding and upgrading data or schemas in existing databases, tables were not allowed. So we were not able to version data using, for example, timestamps. And for moving the data, it is pretty important. So with such kind of limitations, we were not sure, is it possible? Client was not sure, is it possible? But so when you don't know something, you never sign the project. You sign up for discovery phase. So our research and feasibility study and our assumptions contained of several topics, like incremental replication of on-premise MySQL database to the cloud. One, feasibility study of change data capture tools, if it's possible with such limitations. Second, research of custom solution for parallel dump, for God's sake. We tried in that. Feasibility study of pushing bin logs. I've talked about what does it mean going forward. Research some vendor solution, but the current vendor solutions are more like platform centric, so it's always pool. Doesn't work. Design ingestion storage layer. It's for streaming, and it's something that we also took going forward, and of course provide final report if it's at least possible or possible in reasonable amount of time. So I will talk a little bit about details of how this research was done. And first, what we need to know is binary logs. So this is one of my favorite topics for the interview of data engineer. Asking about how do you think ACID transactions are implemented under the hood? And they, ACID, this acronym. I said, okay, not interested. How is it implemented under the hood? I'm giving an example. What happens between begin transaction and commit transaction? Where data resides? How you're able to validate that query is valid without data being in database. And if it was a rollback during this execution, the data won't ever be in database, but it is possible to validate it. So where that data resides. And some answering this, maybe some cache, RAM memory, but RAM memory is dependent on electricity. And what happens if during the transaction light goes out and this breaks consistency? So the right answer is that data is stored in binary logs on HDD drive, SSD drive, but not dependent on electricity. And in the same way, read replicas are created. So not to put additional load on the master database. It's pretty important. Yeah, a little bit of information on binary logs. And there are two types of binary logs. First is statement-based, so you log actual SQL statements that were executed on database. And that was obvious first solution. That's why it's also legacy solution. And the second option is row-based binary logs, which actually logging of all rows that was affected by one or another query. Who can imagine what was the problem with statement-based logs? Any?
You don't have consistency because you don't have an access to data, actual data. You have only changes.
Yeah, but it's like both binary logs has only changes.
Fair enough.
The thing is that not all statements could be reproducible. For example, if you don't have order by, if you have update with limit, such cases leads to that statement-based bin logs not always reproducible. That's why currently in all databases, transactional databases, row-based bin logs are being used. And that was the real pain during the investigation, because they were not able to change it in reasonable amount of time, because all their monitoring tools and everything was, backup restore tools, which were proprietary, were taking into consideration that there would be statement-based logs. So it doesn't work. Diving into the topic, I felt like Rick Grimes. My SQL 5.5 came up in 2010 and was deprecated in 2018. As I've said, not all statement-based bin logs could be reproducible. And row-based bin logs started to be more or less standard since 2015, which led to a picture like that during investigation of different CDC tools. If you can see this like red dates, which is basically end of support of different tools that worked with statement-based bin logs. And 2015 was kind of the end of them. Row-based bin logs became standard, and all other open source tools, contributors dropped the support. So yeah, after understanding this, I felt like this guy on the beach, putting a sand to the head. So what to do actually? Because well, it's kind of it. So you have to use only statement bin logs. It's not supported. So and it's really risky to take some legacy technology in big data world. Yeah, but then I've realized some binary logs like used for CDC, but they kind of used also for another technology, and So replication. So we decided, if the master databases produce only statement bin logs, why not to create replica? So limitation was that we could not influence master databases, but we could work out with slave databases. That's why we came up with the solution. So we set up similar servers, on-prem infrastructure that are listening to statement bin logs, replicating the database, but by themselves they are producing raw-based bin logs, which could be consumed by any modern change data capture solution. And came up with implementation candidate. So we have master, we have slave, then one of change data capture tool, which streams changes to Kafka, and in the end to S3. So seemed pretty okay for us. And in a while, so we had to also come up with the change data capture solution that we want to try. There are quite a few on the market, and yeah, I've listed all those in presentations, but we took like the most obvious candidates, maybe not obvious, but most promising candidates, and it was Debezium, StreamSet, AWS Database Migration Service, which is like the DMS, and Data, which is appeared to be also a platform, and then pulling the data, as well as Database Migration Service. So it's a service in AWS, and since it's in AWS, it pulls data from on-prem, which is was not feasible for us. So Debezium and StreamSet. While investigating those two tools, StreamSet, by the way, has pretty great user interface. So you can do kind of data pipelines in visual manner. But in terms of like best practices, information about the framework and its scalability, Debezium was like #1 choice. So we tried StreamSet, but decided not to go forward with it. But I know there are companies out there who do similar solutions with StreamSets, but all are on slightly lower scale. So the Debezium. Debezium is basically like a platform, a solution that provide you with ability to reliable moving of changes of data from OLTP, like transactional processing storages, to the Kafka. And then you could do a variety of things with this data. So our schema was that there are slave databases. We set up another server with Debezium inside, connecting to those databases, streaming the changes to Kafka, and then to S3. Debezium under the hood is basically Kafka Connect. So it's more like a facade over the Kafka Connect. And this technology really reliable. So you can rely on community of Kafka Connect, so that all the changes would be streamed in high available, reliable, durable fashion, because it's Kafka. Yeah, and so we on this stage we thought that okay, we have the solution. Let's go implement it. And but the client came and said, okay, we are working on pretty large scale. And on our scale, situations like a server goes down, so a server burned up in the flame is not extraordinary situation. It's something that we deal on like weekly, monthly manner. So the solution itself is not that interesting to us. Proof that it could be highly available. And we brainstormed with the client and came up with something like 15 use cases that we need to check. Those use cases were something like, well, first to just set up and validate that it flows. Then restarting slave with the Besium running. So for example, if slave database restarted, what if master database is not reachable? What if Kafka connectivity is not there? What if the Besium server goes down? A lot of such use cases. So even something like, okay, we stream something to Kafka, then the whole data center is not reachable, and then we start again. Is it possible to get all the data that was on like 1 day long when the connectivity? And it appeared it's possible. So we checked all those cases. First, we've done it on our Dockerized environment. So we're producing all those in Dockers, and then came up with also a demo stand in AWS. So spin out EC2 instances, and it allowed to work with actual dumps, the real world dumps that they have there. So we created like a sample script that we're taking dump, create a database from this dump, and then we could check the whole flow there. And we thought like, okay, who's your day? We've done it. But client again came and asking, tell me about the incremental processing. We heard there are other tools that will make our data lake work like a database, which we kind of need, because most of their jobs was Presto, was Hive, so need to support SQL-like syntax. And we again we spin up our environments and continue to investigate. For the incremental data processing, there are currently 3 players on the market. It's Apache Hudi, Databricks Delta Lake, and Apache Iceberg. All of those solutions are even relatively not near those players, and we started to estimate those, evaluate those. What you expect of your modern data lake. So you expect that there would be ACID transactions. Yeah, you expect that data could be changed in a while. So data mutations. You expect that it could be work with batching and streaming, because you don't know in advance what you would face in the future. Of course, storing metadata, because you want to do something like time travel. So querying the data not only on current state, but also in a state like week ago, be able to go to this checkpoint. Data quality is also pretty important. So you need to be able to check what you actually consume in the data lake. Pluggable storage, so the solution should not be dependent on some vendor storage, which is basically really bad practice. and yeah, independence of processing engines also. In addition, yes, something like schema evolution, so databases changes. That's the main point of those, and schema enforcement. So if you like getting for some reason data with additional columns that you do not expect, you enforce the schema and store only the data that you expect. Not to, those are not conflicting ones. So if a schema change came from the database and you handle it, then new data is fine. If it was not done with DML statement, then it's something wrong, maybe network connectivity. Yeah, so, and that was like comparison of those tools. I won't go like for each line. All three tools were like good choices. So it's not something that we chose only one because two other candidates was gross. So almost they covered almost all points that we expected from them. But the conclusion was that Delta Lake is great, integrating with the whole Spark ecosystem, but it's pretty dependent on Databricks, at least on that point in time. It could be distributed separately, but for cool features, it was dependent. Apache Iceberg was great by design, pretty interesting, but what we understood that community is not there yet. So it was something like 40 people of community on that time, and we decided that it's pretty risky to go with this solution on that stage. Currently, I know that some big companies use Apache Iceberg for similar solutions. Pretty happy with that, but still. And Apache Hudi, something that we've chose. It was also like the best candidate to work with streaming. For example, Delta Lake on that stage worked mostly with batch ingestions. So Apache Hudi worked with streaming, had a special ingestion library, Delta Streamer, and what was also very important to us, starting from EMR 5.28, Hudi could be is there out of the box. So you set up EMR cluster with several checkboxes. I don't remember right now. It was like 4 options you need to check in terms of Hadoop ecosystem to be in EMR, and Hudi is not one of them. And if those are checked, Hudi is already there, and you can start doing your pipeline with EMR, which is really fast. So you don't need to set up it. But yeah, there was some trick. Hudi there was pretty outdated. So we had to wait for quite a while to cover all. Guys, are you still with me? Yes? Okay, great. Then let's continue. Apache Hudi, which stands for Hadoop, Absurd, and Incrementals. But I'm pretty sure they came up with that much later than the technology, because I know that while it was in Uber, Hudi was written otherwise, with double O, IE. So that's marketing. As I said, it was created in Uber in 2016, and 2017 it was open source. And on that time, it already worked with 100 petabyte data lake of Uber. And it was promoted to top Apache projects in 2020. So when we were doing it in beginning of 2021, we felt like early adopters of the technologies, which was obviously not that dramatical, but still. So it's kind of a high-level architecture of Hoodie. Could like you can ingest data real time or like pipeline, like more batch fashion. You can work with data, store like the snapshot of data in Parquet format, and because you're also storing metadata near, you can do something like point-in-time querying in the past, time travel of the whole database, a lot of cool stuff. What else important here to tell? Yeah, and there are several types of queries, and we come later to that. There are two types of organizing storages, which is called copy on write and merge on read, which are basically, yeah. So it depends. You choose one or another, depends on what situation do you have. Here is an example how it works. So copy and write is basically when you, so at first you have A, B, C, D, E, then you update D and A. And while you're writing those updates, you're also creating the new files. Yeah, so when you do read optimized querying, you query a new version of the file. But also you can query only incremental, only changes, and that is something that was pretty important to Uber because they used Hoodie for tracking of the rides, yes, taxi rides. When you have continued like a car driving, and you need to track all the points it was there and the current state, and you should track it in on enormous scale. And obviously, if you're tracking everything, you want also to receive the latest state. Yeah, so you don't need to query the whole path during the ride. You want only to know the latest point, and that's how incremental works. And read optimized is querying the data in current state. So pretty similar to database. So it's basically a snapshot of database in our case. But you're doing that when you're working not on the big scale. So you don't have like million records coming in your database. Your workload is pretty predictable. So you know that, for example, you have hourly dump of data, and you can handle it in similar fashion. Because if you know columnar formats and Hoodie store data in Parquet format are great for training data, but it gives a lot of load if there are a lot of updates. So you need to write files a lot, and for large files, it takes quite a lot of time. That's why they have second option, which is merge and read. It works with Parquet format on storage and Avro format on the income. So both are binary formats. The thing here is when the new update is coming, it's not stored in Parquet format right away. So they store something that is called delta commit. So you have those changes stored in your data lake, but they're not yet in Parquet file. So you can customize how much of those delta commits you can store in time and in terms of space. So it's all customizable. And there is new mode for querying, which is real time. The trick is that incremental and read optimized work pretty similar. So they query upon the file. So when the actual Parquet file is created, so they work, well, incremental works on the space. Yeah, well, update is coming. But grid optimize queries only the state, the current state of the storage Parquet file. Yeah, I understand. Real time is basically working on those data commits. So having like a lot of load data coming like on enormous space, but you're still able, even not storing it in Parquet format, you're able to retrieve the current state of data in data lake, including other files. And that's like was like kind of magic actually for me, but yeah, it works like that. Uber, thumbs up. Yeah, so you use it if you have, but yeah, the down like shift of this schema is much more complex, obviously, and it's hard to understand, hard to implement, but it works best when you have a lot of data, a lot of load. You have unpredictable spikes in usage of your like service, like for example in Uber. Yeah, so they could have spikes during like concerts, during morning. I don't know, it's pretty predictable, but still. So if you have spikes, you need to handle it with data commit, because this makes it possible not to do the compaction each time. Compaction. Compaction is getting the initial state of Parquet file, all metadata, and then optimize it to be stored in the single file. That's what compaction is.
Easy.
Easy peasy. Mine is easy. Delta Streamer is like a library, a connector that makes it possible to work with streaming on large scale. So you can work with Kafka, you can work with Hive if your data lake is HDFS, and it has even connector with S3, so you can take data directly. And that's how we were doing the first tries with this technology. So yeah, a lot of good things that Delta Streamer provides with like schema evolution, checkpoints, rollback, recovery. So it's a really mature technology. It can bring high availability in your data lake and ACID transactions. Yeah, and afterwards I feel like, yay! All the research took 1 month and effort of 2 solution architects, and I was one of them. It was pretty time constrained because we said that in 1 month it would be out there. And it was pretty critical for the client. And it made us possible to come up with statement of work for the implementation of pilot project, which looked like this. So on-prem, 2 servers, it's master, then replication for raw-based bin logs, consumed by Debezium, pushed to Kafka. Schema changes is pushed to schema registry, which was also like a big pain to reach because Kafka was behind the like internal load balancer, but it's the point of other talk. And after that, reaching up through the hoodie in hoodie table and snapshot table from which Hive and Spark would take the data, query the data with the time travel. Time travel, for you to understand, it was pretty important because they want daily analytics. And it is streaming. So this app, when you have nearly 10 million of daily active users, the app never sleeps. But they want daily analytics. also in terms of like checking if we like Provectus did the right thing. So they had analytics for the snapshot. We also compared it using Hoodie. So to do the time travel for like midnight of certain days and do the data analytics there. And even going forward, we came up with such architecture for sharded databases. And as I said, having come only with research on something like 50 slides, I decided for the actual implementation to be in my next talk because it's too much already, but without the context of the technologies, what we've chosen, and context about the client, it was pretty impossible to tell you about the implementation itself. Yeah, a cliffhanger. So yeah, what in the next episode, it would be information of how we set up the environment under hostile conditions, of different departments fighting for responsibility, how we overcome unexpected issues, and we even had a log of all the issues, and it was something like 34 issues that took us more than 1 day to resolve. How to mix up with estimates but still bring value to the client and the company. How do consistency check on running production workload. I've touched that. So stay tuned for the next episode. And but still, I need to do some sum up for this talk. What you should take from all this discussion. So always architect for high availability. It's coming by default in big data world. Nobody needs the solution which is not stable on any scale. Make a test stand to what's called fail fast. Yeah. So Docker environment, you can check some of the assumptions right away, even locally. So Docker environment, do demo stand on cloud dev environment to check, because well, we face something that locally it works differently than in the cloud. Of course, because like cloud Hoodie had different version. Keep it in touch with client always to understand his expectation early in the cycle, not provide the whole report and then doing it all over and over again, maybe even without the necessary context. Always have several options in mind. So you could switch between them if the context is changed, if some limitation has changed. You need to have several solutions in mind to be successful. Be flexible to shift. So not holding some solution, even if you think it's really great, but doesn't work for this client. So be flexible to and document everything, because, well, 90% sure that you would, okay, 1 week ago we tried something and it worked better than today, but what was it? And it's quickly becoming a mess. And most important, never give up. So there are a lot of technologies nowadays in big data world. There is high probability that you face an issue that somebody faced before and solve it. So never give up. Be in the community, knowing like new technologies, being like in AWS blogs and everything, and you will find the right solution for the company of the certain scale. Oh, no. And yeah, so IBU said that life's better when we're connected. So connect to our social media. Let's keep in touch for, again, next episode. And questions? Questions?
Too many buzzwords. Just need to warm up.
Yeah.
What is the most problematic things in all this system?
If I would choose one, I would say data quality. Because yeah, we've set up all this top infrastructure, starting to get some data, and only when we start comparing, we understood what trash was the source. And you even said, yeah, we know, but it just didn't work. That's why we had to come up with certain adjustments in Debezium, and it is possible to do it in Debezium. So, for example, they had 0 dates and null dates. Null dates is what null, 0 dates, and all digits are zeros, and it was different. And for standard Debezium, it thinks, okay, 0 date, null. Go. And it broke some downstream jobs on the term. Unicode. So it was something like, okay, in this table we have difference like 75 million rows of difference. In what column? Comments. Spanish comments. Okay. And by the way, the right special letters was valid in Jordi, not on their dumps. In their dumps, it was like a mess. They just never analyzed those, but still. So yeah, data quality was real pain. And the scale was a real pain because initially for understanding to which topic and shard of Kafka data should go, we used timestamp. In a while, we saw that there are differences in data and understood that the updates for the single row comes within the same millisecond on the scales from different servers. And Jordi was unable to understand which to apply first. So it was pretty probabilistic. Then we added to the hash, we calculate hash based on timestamp together with row number in binary log. And that solved the issue. But it took quite a while to understand even what the problem is. Because at first it looked like magic. In one row, everything's fine. Other row, it's not. So we erase everything, doing vice versa, doing it again, and it's quite opposite. So now in this it is wrong, and this is fine. Fine. And like working on terabyte scale, it's pretty tough to investigate each row change. So yeah, that was the pain. Any other questions? Yeah.
If I get the idea properly, you have a division that is connected to different slaves. So could you have a situation where you have a lot of data that are duplicates, and because the same slave can have the same data, and if I get it properly, division reads binary files and can encounter a situation when it reads the same data or same updates. So how do you manage these duplications?
Okay, we had only one slave per MySQL database, or for sharded databases, it was vice versa, like aggregation. So one division for several shards. One slave for several shards of master. But yeah, it possible in terms of duplicates, but Jordi can solve it. So the same role, like with exactly the same like timestamp and row number for it, it's like the single data.
Okay.
Yeah, so it creates this ACID-like transactions based on RDFS name. So it's not possible to be like this.
Which mode eventually you pick it up, work with it?
Which mode?
Right? So like version reads or like a copy on writes? Like which one you pick it up?
It was merged on read. It was merged on read, but we took two approaches. We've done snapshot, the initial snapshot of database in batch mode, and then we were switching to streaming mode because initial snapshotting was too long in streaming mode. So we decided to go. We took some heuristic of 100 million rows per one batch, and that was the most efficient one. So we took the all data in Kafka on the level of 100 million rows each time, process all the data for the database, and then we were shifting to streaming mode for that connector, reading the updates.
I think we should wrap it up.
One question. If you say what was your biggest risk and what was the lessons learned from it? If you consider the whole project.
The biggest risk was that, well, it's open source tool, and there was a case of merge on read in streaming mode that we know that there is an issue there for quite a while. So we knew that before we starting doing the pilot, hoping that it would be resolved till when we come to that point, and it was not resolved. So we have done a little bit otherwise, the one that shifting from batch to streaming mode afterwards, and that solved the question. But on some level, we even put something in SOW, like we are not responsible for if some open source or AWS service is not ready for this type of technologies. But we were able to overcome the idea. But yeah, in open source technology, it could happen that something is not implemented yet.
So lesson learned, do add to the SOW, save your ass, right?
Yeah, if you know it in advance. Yeah, for this particular line, after the research phase, you saw that there was a lot of additional stuff. So it was the only SOW in our company where the list of what we will deliver was less of what we won't deliver. It was something like 11 points of what we won't deliver during the pilot. Okay, so thank you being with me for the whole talk.
All right. Hi, everyone. Thanks for being here. Thanks for inviting me. It's a pleasure. It's an honor to be in this first session of this meetup. I hope the talk is interesting. My name is Jordi. I'm the head of machine learning at Provectus. I do special projects and stuff like that. I don't have a slide, and I hate to talk about myself, so I'll just talk about the problem. That's what I like. The title of the talk is Sometimes You Succeed, and Sometimes You Learn. And we will see why. And I will be focusing on a use case from the insurance industry. It's just an excuse, but it's a good excuse. Now, of course, okay. One quick word about Provectus. Basically, work on data problems. We pride ourselves on working with precision. The key point is that we have a lot of referrals from clients that are happy and they send us more business. So that's a very good sign that we do things well, and we can claim that we work with precision. We love to use machine learning and artificial intelligence to solve complex data problems. We have offices all over the world. The headquarters is in Boston, but right now we have people all over Europe as well, Latin America, Brazil, Peru, El Salvador, and now a lot of people here in Poland. And of course, like main projects, or at least two cool projects, Giphy, if you use Slack, Giphy, and SUS Health. I didn't know SUS Health, but it's a big healthcare company. Just to be clear, the data that I will be showing, not from SUS Health, different story. But yeah, check Proxet out, please. It's a great company to be at. We're always hiring. We have lots of openings. If any of you wants to move into some kind of data analysis, data science position, just come talk to myself, Ina, like, please do. We always welcome new talent. Now, in this talk, I want to focus on these key topics for today: high data, enterprise clients as a use case, and resilient solutions. And this is going to be important. I'll show how. Plan. I want to introduce the client and the need. I want to understand the challenge, why we thought that we couldn't succeed in this case. I want to walk you through a possible solution, something that I came up with. Still not sure it's possible, but it works in some interesting ways. And I want to do both the proof of concept in terms of validation in behavior and performance, because basically my main solution, this proposal is going to be about performance. So I want it to be well performant. Finally, we will be applying the solution to this insurance data set and have some fun. We will see some cool examples. At least I think they're cool. And finally, some quick recap and some summary. Okay, the client, large American health insurance provider with lots of data. So in this case, scale will matter. Now I know I would just need to talk to Alexey for him to fix all the problems. I have no idea how to work at that scale, but I see that it's possible. Anyway, scale will matter in our case, but it's not the main concern. The key point is that, that this company wants to build an anomaly detection system, okay? And just to go straight into the question, the main problem here is that usually anomaly detection, we will see an exception, but generally speaking, implies going through a vast search page. Basically because we don't know what we're looking for. So we just look for anomalies, okay? But there are so many different kinds of anomalies. What are you looking for? We don't know. We just scan a lot of data and try to find meaningful patterns, right? That's the challenge here. It's going to be how do we scan enough data so that interesting things come up. The use case for this company was, imagine that we have a single Spanish-speaking doctor in southern USA. This can happen. Like small town, there is only one doctor who speaks Spanish. There are a bunch of Spanish-speaking patients in this practice. This can happen a lot because in some places there are actually more Spanish people than Americans. And what happens? The practice closes. And as it closes, all those patients stop paying because, of course, why would they pay for a service that they can't get anymore? They were insured before, but now the doctor who could talk to them is there no more. So they just, give up their insurance. Now, this is a small change, just small change for one doctor in a town. It can be dramatic for the town, but on the overall scheme of the whole company, they don't even notice this. I mean, unless somebody raises an issue or says something, or you have some kind of alert or warning, why in this particular town, right? This could happen, nobody will know. And the key thing is that if this same pattern, this really tiny change happens all over your data set in many different places, you just won't notice anyway. And at the end of the year, when you get the results aggregated for the whole company, you will see, oh my God, what's a drop? You will have a drop, but you won't be able to trace it back, at least not immediately. This is what the company wanted to track. These are the anomalies that they want. Things that may be fine, too small to detect, that end up building up to a big change, but that you can't even define in advance because you don't know, okay, like this guy here is going to retire and he spoke Spanish and we didn't know. So anomalies. Now, well, this is generic anomaly detection. Of course, this is the use case. This is why it's important. You can also use it for credit card fraud. It can reveal a bug in the protection system. It could give you early warning for microtrends, as Alexey said before. In case of Uber, it could be a concert, right? There is a concert, something's happening, you have a spike, all of this kind of anomalies. And as I said before, the key thing here is, okay, how you define anomaly? Because you don't know what you're looking for. So maybe you have an idea of what's normal distribution, and good luck still trying to define that. And based on that idea of what's normal, you can then define, okay, whatever is not normal is anomaly. That's probably your best chance. Still not easy, because these are all the different definitions that people have proposed for anomaly, right? Or anomaly detection. And so it may be an outlier, which is an observation which deviates so much from the other observations that are as a suspicion, or an observation, or a set of observations which appears to be inconsistent with the remainder, this idea of the normal distribution that we just came up with, all of that, right? These are just a few of the definitions, actually. Key points here. These are for me, the key terms. And in this, I don't like this, like one observation, no, not really one, it could be a bunch, actually, it can be a macro trend. One observation is just an outlier. And for me, that's just data cleanup. You know, you define some threshold, whatever is X times the threshold, it's probably an outlier. I wouldn't give it a second thought. Of course, many are important. You still want to track them. Big changes can be meaningful, but this is not really what we want here. My guess would be these are errors. I don't care. I still want probably a subset of data points. That's what I'm interested in. And at the same time, I don't want this idea of deviate so much. It will deviate, but it's probably not going to be obvious. It may be obvious at some scale, but you can't just rely on the fact that it's going to be huge. Maybe it's huge at a very specific level, as we said before. For that small town with that Spanish-speaking doctor, the change was huge. Yeah, once you already know that's the space you need to search for. But when you're searching the full space with all the features, that doesn't even make it. So you can rely on this idea of big deviation. Could be small. You still need to track it if there is a consistent behavior. So that's the key point here. We want to track not outliers, that's just data cleanup, but rather variable sized sets of observations, as long as they are consistent with each other and more consistent with each other than with the rest of the average population. Let's say what you define as the normal distribution for these things. This is our key thing. This is what we're looking for. This is our definition of an anomaly. And this, of course, since we define a normal behavior and we have a prior expectation of what that is, basically, we can talk about belief, and whatever you talk about belief, you can talk about Bayesian statistics in a probabilistic framework, which is what we want to use. And, okay. Now, all right, and just to wrap up a bit more the challenges with anomaly detection. First challenge, requires unsupervised data. Why? Because of what I said, unsupervised learning, sorry. Why? Because as I said before, you just don't know what you're looking for. So you have to be open to any kind of anomalies. In some cases, you may have data, then you can train a model and so on, and just use standard machine learning, but not, that's a rare case. At least it's not as interesting for me. And for the same reason, you don't have enough data. So yet again, unsupervised learning. So I think the solution for this has to be unsupervised learning, at least for it to be meaningful. Again, not saying that there is not anomaly detection that happens in machine learning, there is, but more interesting for me is when you don't know anything about the problem and you need to figure out, okay, is this weird or not? Clustering could be relevant, and actually it's used successfully in some cases, but it suffers from, the main problem is that it suffers from the curse of dimensionality. As I said before, if you have a huge search space, let's say 100 variables, you have a big matrix, a big table with 100 variables that you can track. And if you use clustering, there is a good chance that many relevant fluctuations, many different changes are not obvious when you consider the whole vector. If you were only considering some subset of columns, feature selection, whatever, correlation, some kind of multivariate analysis, that pattern may become more obvious. But if you just, average it across the whole vector, probably the distance is not going to be big enough that will make your trigger, that it will trigger your warning system, right? So that's the key problem here. Usually, many clustering algorithms just see outliers as noise. They don't even consider them, either exclude them explicitly or just don't have enough resolution to find them. And this is another key thing. The core idea, again, is that we don't know what we're looking for, so we need to explore all the possibilities, try all the different combinations of variables, and that's what has a high computation cost. And before getting there, let me say that this was the problem with the client, and it was actually the not succeed part of the title. The client wanted this, and we just weren't sure we could deliver. And as Alex had said, just don't commit if you don't know that you can do it. And we couldn't. There was actually two teams in the company. Some people thought it was impossible. Some other people, including me, thought, we don't know. It's probably worth a pilot, it's probably worth a check, but we really don't know. And because we didn't know and the company needed an answer, we decided to tell them, look, we don't know, but we offer to this pilot. And they went with a competitor. That's the not succeed part. What this told us is that, okay, there has to be a way. Like if somebody can promise they do this, assuming that, you know, they're doing the right thing and they're not over-promising, it means they have some way of doing this. So what are we missing, right? That was for us the key learning point. It's like, so somebody can promise that they can do this, why can't we? And why were we so convinced that this is not possible? From an engineering perspective, if you have to explore this vast search space, basically you're facing this formula. I don't have time, I won't focus on the details. Let's just go here. This is the important part. That's like hands up. How many people understand this more or less? Okay, a cluster here, a few people here, okay. All right, I'll try to explain it the best I can. Probably a good question for later here, okay? So, mental checkpoint. All right, so again, matrix, big matrix with a lot of variables where we need to find anomalies, okay? It's dimension, each column in our matrix, okay? And this is every value in each of these columns. So we need to explore this whole space. And at the same time, we need to explore every combination of those columns. So imagine you have 10 columns. You want to check every two, okay? The first with the last, the second with the last, the first with the second, all of that. That's this part. In this part, you just take all the different values in the column. Sorry, it's column. And here, all the values in that column. And the problem here is that if the column has a continuous value, basically, you need to slice it because basically there is nothing you can discretize or iterate over. So what can you do? In this case, something simple, we're going to bucketize everything, right? So imagine we have the full set of values. We're going to create maybe 10 buckets, top, highest values, bottom values, another 8 in between, and we're going to iterate over that. This is our search space, okay? We're going to try many different combinations of every column and every value in that column. Now, the problem is that when you do that, basically you need to multiply first the columns, the values, the values in the columns. Let's say that you have one column with 10 values, okay? After discretizing, bucketizing, all of that. Another column with 10 values. And you need to compare all of them. So first value in one column with every other value in the column. 1 times 10, 2 times 10, and you end up with 100 combinations, okay? So that's here, 10 times 10, 100. If it was 2 values in one column, okay, that's only 20, but still, this multiplies. So as you increase the number of variables that you consider for each possible combination, it's going to grow larger and larger, and it's going to become a problem soon. Probably you shouldn't go any farther than, you know, let's say 10, that's probably too much anyway. It's 5, 6. The key thing here is how many variables do I need to define an anomaly? That's the key point. I'll get back to that later. For now, just remember that here we're multiplying a lot of different columns and other variables, or the values, sorry. So that's going to be a big number. And this is for the different combinations, right? When you're doing combinations, this is not permutations. So order does not matter. We only compare unique columns. So each column only once. That's slightly better. No replacement either. But still, we're doing all the possible combinations. So if we have 100 columns to start with, not pretty. This number is just intractable. But let's say you can group them into maybe 6, up to at least 1 digit, no more than 1 digit, right? And ideally 5, 6. In my laptop, I've been able to get to 5 to 6. Here the key is, okay, if I have a bunch of variables that deal with time, let's say week, quarter, stuff like that. And again, you apply discretization. And let's say you have another bunch of variables that deal with money and so, right? And demographics. Then what you do is you keep each of these slots for one of these groups of variables, right? And then that's what you combine. And if everything goes well, you won't have more than, or at least you won't be able to deal with more than 5, 6, 7, probably tops, such combinations, right? But this allows you to break the problem in a way that, okay, I know that I will be eventually be able to compare every variable, every separate variable in my model that can inform the others. Because sure, different financial variables, some may be not correlated, but a few will be correlated. You don't need to compare those, just one at a time. And the same for demographics, and the same for business, whatever, geography. So just consider one at a time. That narrows down the problem here. This term becomes smaller, and still, it's going to be a big number, that's for sure. But you start getting it under control. There is, though, a further problem that we will look into that still makes this intractable, because it's very easy to get in the millions here, in 1,000 here, and basically you're dealing with billions of combinations of values. You don't want that. How do we solve that problem? This is what I just said. I don't think we need this right now. We may come back to this later. Okay. Yeah, it's what actually, right. Yeah, this we need. We're going to define this anomaly score, which is just the probability, the joint probability divided by the independent probability assumption, okay? For all the variables that we're considering. So let's say we have 3 slots. We're considering all the combinations of 3 columns in our data set, all the variables. So that means that here we're going to multiply 3 variables. Here, the joint probability that this particular combination over entire data set, these values, right? And what it's going to tell us is that it's kind of like the mutual information, not exactly, but a bit the same idea. It's like how related these variables are to each other. We are comparing this to what will happen by accident, right? Like if we had the first variable just, with the probability in the normal distribution, and the second variable with its probability in the normal distribution, and so on, we would just expect this amount of cases over an entire data set. But now imagine that we are actually observing many more, okay? That means that these variables are indeed correlated. That's the mutual information measure. So this is going to be what tells us this is anomaly. If this score gets greater, let's say, than 2 in this case, so double the normal probability, or less than half, which means that it's actually kind of an inverse correlation, so to speak, it means that it's an anomaly. Otherwise, it's just fine. So basically, if the score falls within this range, we ignore it, not an anomaly. If it falls on either side, it's an anomaly. And we basically flag it as a positive for now. The key thing we're going to do is learn from this and say, every time we find something that is not an anomaly, we're going to learn that that's a rejected hypothesis, okay? We're going to store cache and reverse index that particular combination of variables so that whenever we are analyzing any higher order variable, we're going to skip this one. Because we already saw that this particular combination of variables was not meaningful. There was no mutual information. This particular combination is not interesting. So we don't have to compute it even as part of a bigger variable combination. We can just skip it. If there is anything to be learned in that higher order variable combination, we can learn it from the other variables that we haven't excluded yet here. So basically, we're going to use the path that the anomaly is defined for us in the data to get to the other anomalies faster, pruning everything else. It's going to be a very aggressive pruning that is going to discard a lot of the search space. Now, I know what you're thinking. It's like, Jordi, this chart is not complete. There's missing data here. That's the point. So blue is with pruning, right? What I just discussed, this idea that we're going to save operations. Red is without pruning. So we're doing every combination, every column, every variable. And what happens is that at this point, I stopped 2 processes. This is 90 minutes, okay? And in 90 minutes, this guy got to here, whereas this guy got here, right? Linear, sublinear, actually probably faster than logarithmic scale. And the key point here is, as you can see, basically average here is probably 12, average here is probably, 3. So you would expect 4 times this, let's say 1, 2, 3, 4, more, right? Yeah, exactly, this is the space this would take. But as it learns all the refuted hypotheses, just look at what happens. These are actually computed. This is just the system saying, no, I don't need to do this, I already know there's nothing here. Nothing here, nothing here, nothing here, nothing here, something small here, and here, there is something. But we're just skipping all this huge space where we know, no, we already did it here at this learning point, and after that, we can just skip. And this way, the process can use the information it learns through the anomaly detection steps to inform its own work afterwards and become so much faster. And I like this one. It's like red and blue are the same. It's just that now it was over 20, now it's over 40, but it's just the same. But these 2 lines are the cool ones. This is all the refuted hypothesis. Okay, so all the variable combinations that we know are useless. And these are all the combinations that we are not doing. We are just saving. This is times 20,000, okay? Over 40. So here it's almost over 1 million combinations processed. Most of them are being skipped. We don't even need to handle them. And we still are recovering about half of all the anomalies. Like this guy here would only find twice as many anomalies as this guy. I still don't know if they're more interesting, maybe not, maybe yes, but still, we have insane recall for the performance boost. So it was, again, I'm not sure this is what our competitors were doing, maybe not. It's the way so far that I found to be able to more or less handle this kind of indiscriminate, search space walkthrough. But it says to me that something may be done, with good caching, with reverse indexing, and all of this, discretization, probably there's something. Okay, just some estimates. Performance is not great. I think there's still room for improvement here. In my estimate, I think we get to 1 million records with, right now this is with Python, right? This is my current configuration. So if we switch to, let's say, C++, that should be at least 10 times faster. I think sometimes it's 20 times faster. It's also my code, so a decent programmer could probably multiply this times 2 as well, times 3. Even more, and so on. So we can probably do, again, not this guy's scale for sure. This is, machine learning, data science, different scale. But still, 1 million records in 15 seconds for this kind of, super aggressive searching, in my case, is reasonable. And we will see some examples that, suggest that there is something interesting here to do that. But yeah, again, in terms of performance, not great, but not so bad as it could be, I guess. And okay, just one sec. Maya, how are we doing with time? Okay, no problem.
You already mentioned that the popcorn slide actually.
Popcorn? Okay, perfect.
No.
Yeah, that's fine. Okay, so very quickly, this was the proof of concept. Basically, in these slides, what I show is that with this purely Bayesian framework, I was able to reproduce the clustering, for the most part, the clustering in the IRIS dataset. Yeah, more or less. Okay. It's a very famous standard clustering dataset in machine learning, data science. Very small, so this is not for performance reasons, but it's very interpretable, and you can easily tell if what you're doing makes sense or not. And in this case, it did correlate very well. It did some different arrangements that I won't discuss, but it found the clusters that are there. And basically, like all these 3 clusters, okay, this was an anomaly, this was an anomaly, this was an anomaly. So basically, without telling anything to the system, it was able to reverse engineer the clustering dataset. That's a good sign. Again, not perfectly, but of course, it has this threshold for the normal distribution. So there were a few core central examples that are not real anomalies. So those are excluded. But the rest, like these and these, are actually for the 2 classes that are farthest apart. It found. And it realized that, okay, this is too far from kind of this, which is center of distribution. So it was actually the biggest anomaly. And that makes sense. So if the algorithm can do this, basically it's telling me that it's doing what I expected. And now it's just a matter of running it over much bigger data. Now, I did that with the insurance data and some interesting cases. Basically, the first thing was what I call the told you so principle. Basically, okay, let me tell you what you have here. What we have here is, in this case, we're looking at these variables, okay? Previously insured. So basically, if somebody already had car insurance, okay, or not. In this case, people who didn't have car insurance. And whether there was vehicle damage, right? So basically, they got in an accident. So we are talking about people who didn't have insurance and got in an accident. Now, why is this here? Because this data is from an insurance provider. So basically, this means that somebody came to them to get insurance after they got the accident. It's like, no, that's not how it's supposed to be. Like, you get the insurance, you avoid the accident, that's it. Or if you have an accident, you're covered. But not like this. Now, so that's why they told you so. Like, you need to get insurance, you need to get, they didn't. Now, important stuff here. And again, this is an anomaly. It's happening about twice more likely than it should, right? So basically, we have a lot of people who get insurance after they have the accident, not the right thing to do. But it's quite common. It's like almost 200,000 cases. talking about anomalies, this is not an outlier. This is not a single point. This is not small. This is like a huge chunk of data. So there's people who, wait too late until they get the insurance. And this is actually super actionable. Maybe this is telling the company, okay, you need to advertise better to these people before they have the accident. Maybe you have to wait at intersections for them to have accidents, whatever it is. But this is probably something they can react to. It's a huge anomaly. It's big. It makes sense even at business scale. And it's right here. It's one of the ones that pop up. And again, 1.7, it's also a nice ratio, but it's not huge. If we remember before, we were talking about outliers as way deviated from the normal distribution. Sure, but sometimes they won't. Like, this is not so dramatic. It's noticeable, but it's not so dramatic. So being able to detect something that is not so far outside the normal distribution, it's still super relevant and it's a big chunk. That's super important. Now, oh yeah, I call this the idiot tax. This is another important case. Basically, I know this one. So vehicle age 1. So this means that they just bought a car, right? In this case, this particular variable is encoded in 3 values only. So 0 is a car that is less than 1 year. 1 is a car that is 1 to 2 years old. So it's almost as bad. They just bought the car. And 2 would be for cars that are more than 2 years, any length, okay? So relatively new car, got an accident, it's come after accident, and that's why you're paying basically 5. Like, this is out of 10, right? So it's right in the median. But again, it's definitely not in the bottom, it's definitely not at the top. It could be at the top, but it's still expensive. It's definitely expensive. Just think, over the whole range of values for premium, which can go very high, this guy is paying half right there. So yeah, not good. So congratulations, that's what happens when you have an accident with a new car. It's like, come on. And again, so basically 4.5, it's 3.5 times more likely that you pay this much money if you have an accident with a new car. And the key thing here also, like this Bayesian statistics model is also good because it can give us an explanation. In this case, as you can see here, it's 11 compared to 1 and compared to 6. Well, 6 is still relevant as well. So basically, we can see that for vehicle damage, definitely this particular premium, the target in this data set, the target column, is going to be high. So yeah, like usually damage means a higher premium. But the key factor is the vehicle age. You're paying more because it was a new car, you're an idiot, so this is what happens when you're an idiot. You pay more. Okay, and Maya, how much time do I have? 10? Oh, okay, we're good with that. Okay, so I can review a few more examples there, which is the fun part, I think. So, again, variables now are previously insured. So basically people who didn't have an insurance in Alabama and are paying actually the lowest possible rate. Interesting here is that there is no age. Age was not relevant for this group. So it's not that, young people who get insurance, haven't paid anything, haven't had an accident yet. Maybe those guys should be paying the lowest rate, right? But no, this is like everyone, independent of age. So it's like, okay, why the fuck, right? And actually, that's a key point. It's like, if they are not previously insured and are paying the lowest rate, this variable, this combination has 61 times the importance than the others. So this is just insane. Like, this just doesn't happen. Like, this is 7 times, so 6.3 times more likely than the baseline. So it's a massive deviation. This actually will qualify as an outlier. It's still 700 records outlier, so definitely not an isolated point. Something's happening in Alabama. But yeah, that's it. It's like super meaningful statistically, very strong association. Again, tied to Alabama. Why are they not paying more? I don't know. That's the key thing. But it's an interesting anomaly. What will happen here is maybe they have some kind of promotion, to attract people in Alabama. Or maybe just Alabama, which I think actually is a poorer state. So maybe, okay, we know we can't charge these people a lot of money, independent of age. So, even if they are not previously insured, we have to, make prices affordable. Maybe that's part of the thing. Maybe in Alabama, people just, don't buy insurance because they are from Alabama. So the only way to attract them is to really lower the prices. This could be different possible explanations, right? But the key thing is that this is going to standardize, okay, this is happening here, something's going on, please look into it. And with the explanations, we actually get a sense of what could be the important things. Of course, the more variables we could add to the matrix, the better. But still, this is the kind of intuitions that we'll get. So really cool stuff happening here. I mean, at least a suspicious operation, something's going on. Maybe there is like somebody in the company has a friend or a lot of friends, and they're just, all of that. It's fair, this will be normal, actually. That's a normal distribution of space. And, okay, I think this is the last one. Why change? Right, okay, 1 sec. Okay, yes, basically here in Missouri, what's happening is that a lot of people who already had insurance are coming to these other companies. So basically they're changing companies. And, oh no, actually too few, sorry. So basically the people, and actually younger people, which is also weird. Why would younger people change companies? Again, I don't know, but definitely doing so half as much as in the rest of the country. So the rest of the country, for whatever reason, younger people tend to change insurance providers on a given rate. And in Missouri, it's half of the rate. What the hell is going on? Maybe, I don't know. Maybe they don't have insurance, they just buy it, they just don't change, they just buy it for the first time. Or maybe they're just more conservative, and once they have a provider, they say they don't care, they just stick with the provider. Again, interesting, because this could tell you, okay, in Missouri, there's nothing we can do, these people don't want to change providers, so let's spend our marketing dollars somewhere else, right? Again, could be actionable, definitely worth looking into. And yeah, it's also interesting from an anthropological perspective, I guess. And there are some more. If we have time, I can come back to this. Actually, I think we will have time. But just to wrap things up, just to do the recap here, and then if you want, we can actually have some more time for questions, or I can explain the things that I didn't explain. Recap. If this, okay, yeah. So key things that I want you to take away, right? In anomaly detection, we will always or often have to use unsupervised methods. As we saw before, we just don't know what we're looking for. We don't have a prior expectation. We may have a prior expectation of what's the normal distribution for our data set, but that's it. Like, how many different ways are there for data points to be different from normal distribution? Infinite. It's like, how do you scan that space? And again, I don't buy that outlier detection is anomaly. No, outlier is a subcase of anomaly detection, but anomaly detection is different. It has to be on subsets of data points, just not isolated data points. It is computationally expensive, as we saw, because of the product that we saw, right? When you multiply all the columns and then the factorial for the combinations, that's insane. But it can be formalized in a statistical probabilistic framework and brute forced with some assumptions if we reject a strong variable dependence. So basically, we definitely don't want to do all the columns because there is not a single anomaly that is going to be defined by all the possible columns of data, right? That's like saying that data is important, demography is important, business is important, car type is important, all of it is important at the same time. Not happening. Probably what's going to happen is 5, 6 variables, up to 7, maybe, very complex cases. Obviously, depends on the problem, but I think it's reasonable up to 5, 6 columns. That makes sense, doable, at least with the given performance requirements. So yeah, that's it. Definitely not the whole list. Now, on top of that, the way to do it is applying cluster discretization. As I said, you just wouldn't be able to iterate over a continuous value. You have to take the columns and packetize them, bin them, whatever, discrete values. Once you have discrete values, you can iterate over all of them. And as we saw before, the key point to get the speed up that we saw in the, right, in the line chart is to cache all the rejected hypotheses and make sure that you don't evaluate any of the hypotheses that contain something that you already know to be false. And after that, once you know that, you can just start pruning super aggressively all the different combinations to skip a lot of processing. If you do that, you will be able to reveal micro and macro patterns, which are the most interesting. As we saw before, 100,000 drivers doing the wrong thing, getting insurance after the accident. Come on. You could discover things like bias and fraud, or marketing issues, or marketing opportunities. And at some point, you can even reverse engineer domain expert knowledge. Basically, you'll be able to tell, okay, younger people do tend to get into accidents more often. Some states just don't have as much purchasing power or are more reluctant to get insurance. All of that, basically the kind of things that an expert will learn about the business over time as they work here. With this, you can get, I mean, of course, not a full picture, but some idea of what's going on fast. Again, not over a terabyte of data, but with an average size data science data set, you will get a good idea. And right, and another cool thing about using the Bayesian framework is that you can get the feature importance scores that we saw, right? That's super helpful to guide the discovery phase and understand which variables are really influencing the result, right? So I think that's very important and very nice. And I know I'm forgetting something, but this is the official end of presentation, but we can keep talking. Just let me think. Well, yeah, no, that's it. So finally, going back to the sometimes you succeed, sometimes you learn. We learned in this case. That's a good part. We can get a client that sucks, but now we have a better understanding of what could be done in this case, right? If the same client comes and asks us to do anomaly detection, okay, we have a few ideas as to what could be done. And if they don't mind paying for a bunch of computers running and evaluating variable combinations, we know we can also do some cool stuff in terms of discovery and exploratory data analysis. We didn't succeed. We are still the coolest company around. Provectus is awesome. So as I said before, you want to work in this kind of problems, this kind of data sets, whatever, try out ideas. Just talk to Ina, to me, as I said before, Maya, they're right there, cluster. You see that anomaly over there? That's Provectus. And yeah, and that's as I said, the official end. So we can try to answer questions, or if you have any remarks or proposals, happy to hear.
Did you measure the performance on the Iris data set?
Not the performance, it was under a second or so. But I measured the clustering, so not the hard accuracy. I could come up with the numbers, I just didn't for this. It was for the clusters, for Setosa, for instance, about 47 of the instances were recovered, which is almost a full class, because it's 50-50-50, right? So you know you have to find 50 examples each. So for the biggest outlier, let's say, like actually, since just one sec, we'll get there. Okay, probably for now this one. So this is Setosa, this is versicolor, this is República. Okay, these are the flower names. This is Setosa. For this one, almost all of them will recover. And as you can see, is the, as we said, the one further up. So the biggest anomaly, let's say. For this was actually the smallest one. I think it got this range, the ones farther from the central. But this central part, most of them, of course, were for versicolor and some for Wiki. And this was the main confusion, which makes sense. That's what you would expect. Not hard numbers, but this is general idea. As a proof of concept, this was like my unit test. Like if this passed, okay, it's fine, I'll do the performance test. If something wrong had happened here, I would have said, okay, different topic for the presentation. But yeah, this was it. Yeah.
Okay, thank you.
Sure.
I have another question. Did you try to use some PCA or TSNE to reduce columns?
No, that would be another option. Yeah, that's totally one thing that could be done. Yeah. Because then exactly, if you end up with, if you already start shrinking the number of columns that way, it becomes so much more scalable. Yes. Exactly. Any kind of feature selection, principal component analysis, absolutely.
Do you know what the winning solution?
Winning solution?
Yeah, because you said that.
For the cuddle.
For the whole problem, because you said you did not succeed with this project.
Well, that's the thing. This was not a postmortem, but you know, kind of had some spare time, decided to look into this. How would we approach it, right? It's kind of a lab thing, kind of a data tool, if you will. So we still don't have an official solution for this, right?
Mm-hmm.
We want. I think there is, as I said, I think there is something here. I think if you make this really scalable, it could be really helpful for informing data science work, right? Doing nothing, just letting the system tell you, okay, I see these things, does it make sense or not? Seems, potentially useful. Again, no official closed solution yet. Maybe at some point becomes a product, but not right now. Yeah.
How much time did you spend for this proof of concept? Because
actually, coding and everything, I mean, the presentation took the longest. 2 days, 3 days. But I already had some ideas from before. But this whole thing, like all the experiments and so on, 3 days. Yeah. So it was reasonable.
And one more question I missed this. So you have used one of the clustering algorithms.
Not for this test. That will be one way of doing it. And for the Iris dataset, it will be the way, because with this dimensionality, it just works. It finds what it's supposed to find, and it doesn't find. But the thing is, it's not as easy for me to do the caching, the inverted indexing, and the speed up after that, right? So when you have many columns, what do you do? That was what I wanted to look into. But yeah, for Iris, dbscan, even k-means, I guess, could give you something.
For me, it was interesting this main problem.
Right. But yeah, that's another thing. Like, just as you could use PCA to decrease the number of columns, probably some clustering used cleverly could also give you, a better idea of where to focus the search, right? Like what columns, what combinations you want to keep following, and then just keep pruning. But yeah, you can make the process even smarter. Yes.
Don't you know your competitors succeed?
We don't know. We don't know. Key question. Because maybe I'm inventing things that are not even possible. Yeah. I don't know. I'll try to find out, maybe. But yeah, definitely curious. Definitely, because maybe they are. Yeah, exactly. Maybe they're hitting this wall, and I can just sell this to them. Yeah. But yeah, no.
What kind of infrastructure have you used? Only locally?
Yeah, for now only locally. Yeah. I would like to run this kind of thing with proper number of machines and so on, bigger data set. Haven't even proof of concept, so haven't even tried. But yeah, would be nice, I think.
And one more question, because I saw the maximum value for anomaly score is 2, but I was trying to understand why.
Okay.
Yeah, that's a good question.
Oh, well, we can use this one. Or
no.
Oh, the formula, right?
Yeah. Here the anomaly score is maximum is 2.
No maximum. Like
Okay.
yeah, actually, okay, this one here is lower, sorry. Let me think. But yeah, actually it should be the not anomaly score. Sorry. This is if this is 1, this is not an anomaly. Okay. So we expect this to be higher. If it's higher, it goes here, and this is actually the anomaly. So, yeah. So sorry for the name, actually. But yeah, it's outside this range, and it can be 2, 8, 7. There was a 70 somewhere. It was insane. Yeah. And then the other way around, if it's you understand. I think that, yeah.
Have you willing to try random cut forest, which is like basically standard in AWS?
Isolation forests or different?
Random cut forest.
No, I haven't heard. I haven't tried and I haven't heard. So happy to discuss. Yeah. I as part of the research, I knew there was isolation forest. That's something, but again, more focus on outliers again than classes of a subset of observations that follow behavior, right? So that's why I said, okay, this is not what I can use, but maybe there is a different random cut thing that I can use. So happy to learn, always. Yeah, thanks. All right, pizza is there. So just, okay.
This pizza is started. Thank you, Jordi.
Sure.
Thanks a lot. I want to remind you and tell that we have this activity that you can share anything, photo, video, something from Jordi's presentation or anything on your social networks and spread the word about our community, about this activity that we started that will help us a lot to spread this information in Wroclaw. And you can win prizes that we prepared for you, and you will receive it today after this final stage of our meeting. Okay, thank you all and welcome.
Guys, who has already made the story